Okay, so uh, there's a really good Jove TLC video that you should watch before we do the TLC lab. But I thought I would show you sort of with the equipment we're using. I'm sitting at the lab bench that we'll be in room 121. And I've got most of the stuff here. I may need to zip off. But anyway, I'm going to run a TLC for you. So the first thing, these are the TLC plates we'll use. You'll see these laying around. And you want to note that it says with UV 254. All right, so that 254 is telling you that you can visualize what's on the plate using ultraviolet light. All right, so you want to be careful with this stuff. I mean, it's not hazardous, but it's fragile. So in general in lab, like you're supposed to be learning specifics about lab, but also generally about lab. Work slowly, be methodical. There's no hurry. I know everybody wants to go home, especially the night lab, but you need to know what you're doing. So don't just do stuff, okay? I do this all the time in lab. I mean, you're human, you'll do this, where it's just like, oh, I'll do this, impulsive thing. Generally, when you do that in the lab, you screw stuff up. We've kind of made this lab, the teaching labs are sort of done so that even if you do something stupid, it's not going to be dangerous. It's not that you couldn't do something dangerous in here, but you'd have to kind of try. But you will almost certainly screw up the experiment, right? Which is just as bad if if this was for real and you really wanted to do an experiment that meant something to you, you'd graduate or you'd patent something, you don't want to screw it up. So move slowly. Think about what you're about to do before you do it, and then do what you thought about. Okay, so I'm going to open up this. It occurs to me I'm doing this on camera now, and this box I've had trouble opening it the last couple of days working out these labs. There. All right, so a whole bunch of TLC plates here. Again, be kind of gentle with them. I'm going to take just one. Hopefully all of you can do this with just one. There's one. Put this back. You guys won't need to close the box up or actually put these back together in any way, but I will. All right, so there's that. And now we're going to write a baseline on it. Can you guys see? I need to make sure my hands stay out of the way. So now you need to write a baseline. So the bottom here, go up about a centimeter and a half. It doesn't really matter how far, but don't go too far up. Don't go too close to the bottom. Right about there is where you want. Let's see, I'll hold this up for you. Right, so you can see the pencil line, hopefully, where I've drawn it. All right, that's your baseline. Then you want to put lanes in. In the lab you guys are going to do on Monday, one lane will be for your leaf extract. Remember to bring a leaf to class. And the other lane will be for your 3-component unknown mixture. All right, so I'm going to put 2 of those down right now. I'm going to have a left and a right, but I'm not going to mark them as left and right. I'm going to write mix and standard. So here's the deal. Here's my experiment. All right, I've got this mixture. It's got yellow stuff in it, right? So I think my hunch is it might be nitroaniline. All right, but somebody else told me it might be acetophenone. So I'm actually going to write a 3rd lane in here. In A and AP. All right, so now I've got 3 lanes. One is the mixture. It's going to be this stuff. One is the nitroaniline, this stuff. And one is acetophenone, which I've abbreviated AP for no good reason. All right, so we're going to have to spot those, and I'm going to run the TLC, and I'm going to see if the spots line up. So first thing, here's your capillary TLC spotters that you'll use. You'll see these laying around the lab. You just kind of, there's a tiny hole in the top. Tiny little capillary. Can you see that? The tiny little capillary comes up. I'm going to move my camera so I can see what I'm on here. All right. Now, capillary action will actually pull the solvent you need up. So I'm going to open my mixture here. You can use either end of the capillary. So, right, I'm going to dip this capillary tube into the solvent, and I don't know if you can see this or not, but that just capillary action pulls solvent up into this tiny tube. And then this is my mixture, so I'm going to put it on the left lane mix. I'm going to spot it. See if you guys can see that. I'm going to spot it gently. You don't want it. You don't want to like mash down because that'll make a very big spot. You also don't want to do it hard because that might disrupt the silica. Just very gently let it dry. Put another spot down. Let it dry. I'm going to say you put 3 spots down. You guys unfortunately will have to be wearing masks in the lab. I have a hard time TLCing with a mask because I like to blow on the plate. So I'm going to put my 3rd spot here. All right, so now we've got our mixture down. I'm going to put the cap back on the mixture. Now, how do we get the standards? So how do I get the nitroaniline standard? Well, you can't spot a pure compound. Okay, so I'm going to make a standard up, and you'll have to do this next week in the extraction lab. We're going to use TLC every week. All right, so there's my nitroaniline. I'm going to pipette in some ethyl acetate. So the other thing is you need to think about these solvents and their structures first, but also their polarity. All right, there you go. So now I have a nice yellow solution. You always want a TLC solutions. So when we add stuff to a TLC plate, it will always be a solution. You don't want to put concentrated samples on there. I'm going to use a different capillary. Again, you'll be able to see this. So, all right, this is hard. Production value is quite low. All right, I'm going to dip my capillary into this. Probably break it. It's got to actually reach. There, I got it. Capillary action pulls that stuff up. I'm going to put my nitroaniline standard next to my nitroaniline, and then go back and I'm going to spot the standard in the lane. So you spot, let it dry. I'm blowing on it to help it dry faster. When you guys do this in lab, you'll just have to wait. Sorry. All right, I'm going to put that capillary in there so I know where that is. And now again, you can't spot a standard. So, like I said, I think it's nitroaniline, but somebody told me it might be some acetophenone. So I'm going to actually get some acetophenone. I have just a tiny amount there. You don't need much at all. You don't need much sample at all in TLC. All right. Dissolve that in ethyl acetate. Again, you want to keep the pipette for the solvent clean so you don't have to use a different pipette every time. All right, shake this up. Need a new capillary. Where'd that go? Come on. All right, so again, I'm going to tip that. So there I've pulled up into the capillary the acetophenone standard. I'm going to spot that in the 3rd lane. If you're wondering about me not wearing a mask, I'm by myself in here right now. Just a little legal CYA. All right, put that standard. Now, if you look at this, you can quite clearly see, maybe you can't. I can clearly see that I've got yellow spots on the mix and the nitroaniline standard, but I can't tell if I've got anything on the acetophenone standard or not. So let me show you how to look at that. So we have these UV lamps. All right, so if I push down on this, I'll get 254 nanometer light. If I push up, I'll get 380 nanometer light. 380 is, and it's not monochromatic, it's not a laser, right? So it's 380 plus or minus 20. So it gets into the visible just a little bit. It looks like a really violet light. The 254 you can't actually see, and in fact, it's very short wavelength and it's damaging. So don't aim it at your skin. Certainly don't look at it. All right, so I'm going to push this down like that. All right, so here you go. And now I'm actually going to turn this over All right, so will this work? Maybe you can see that. All right, hopefully you can see that there are 3 dark spots there. So what's happening is the UV is striking the plate. The silica gel is doped with fluorescein, which is fluorescent. So you should look up the structure of fluorescein. You should look up the definition of fluorescence. The fluorescein will absorb 254 nanometer light. That's a short ultraviolet photon. And then what happens, it's a long story, I'm not going to go into it. This is really getting close to my research, and so I would like to talk about it at length. But the fluorescein absorbs light, the really high energy UV photon. It's excited to an electronically excited state, so a bonding electron jumps into an anti-bonding orbital, and now the molecule has a ton of energy. And its vibration, it gives off some of that energy by changing how it vibrates, like in IR spectroscopy. Now, when it relaxes, when that electron comes back to the bonding orbital, it emits a photon, but because it's relaxed vibrationally a little bit, the energy's different. So now the wavelength's a little longer. And in fact, the wavelength is a green photon. All right, so we see, if you shine 254 onto the TLC plate, you'll see green fluorescence coming back at you. Anywhere there's an organic compound that absorbs UV light, it quenches the fluorescence, so the fluorescein won't fluoresce. And so all of our compounds here, and all the compounds you're going to work with in this lab, absorb UV. And so you'll see the compound where there's a dark spot. All right, now that I've let the solvent dry, so you spot a solution onto the baseline, right? So I've spotted the solution, the mixture solution, the nitroaniline solution, and the acetophenone solution. Now I need to put it in my TLC developing chamber. That's just going to be a beaker, a 250 ml beaker with a piece of filter paper that you've cut the bottom off of, right? So this is a round piece of filter paper. I've cut the bottom off of it, stick it in there. And now we need to make our developing solvent. So TLC, the way TLC works, 12 minutes. Let me just do it, and then I'll explain it while the plate develops. All right, so what I want a 60% solution of ethyl acetate and heptane. So I want the solution to be 60% ethyl acetate, 40% heptane. How do I get that? Well, you don't have to, again, you don't have to be super careful about this, all right? So I'm gonna just shoot for 10 mils of solution. 40% heptane is 4 mils. 4 divided by 10 is 0.4 times 100 is 40. So there's 4 mils of heptane. And again, I don't need to be real careful here. I'll explain what's going on and how the TLC is going to work in just a minute. If you've seen the Joe video, you have some idea. So now I'm just adding 6 mils of ethyl acetate. So I'll have 6 mils of ethyl acetate, 4 mils of heptane. And just get it, reasonably close. I pipette pretty good because I've been doing it a long time. You'll get better. All right, mix it up. Set a watch glass on top of it. Some people, you get better coverage this way. I don't like that because it falls off. Just set it in there like that. That's fine. And now what we're going to do is we're going to set the TLC plate in it. Set it down gently. And then I don't know if you probably can't see this. Make absolutely sure that the solvent doesn't go above the compounds that you spotted. So as you watch this, there's almost no chance this is going to work the way I'd like it to. I'm not gonna bother. When you do this, you'll see the solvent rise by capillary action up the TLC plate, and it's going to hit. It should rise to meet the compounds you've spotted and then carry them up the plate. If when you put the TLC plate in, the solvent is over where the compounds are, they'll just dissolve off the silica gel into the solution and you won't see anything. Okay, so why did I choose these solvents and why do I use silica gel? So again, watch that Joe video. The silica, the white stuff, maybe we'll get another plate here. Again, this takes me a while. So the white stuff is silica gel. And the surface of the silica gel is full of OH bonds. All right, so there are all these OH groups on the surface of the silica. All right, so this white stuff is silica gel. So you've got all these OHs just sticking around. Well, OHs are polar and they hydrogen bond. So a lot of what you read about TLC is about how it's a matter of polarity. What it's really a matter of is hydrogen bonding. All right, the more a substance can hydrogen bond, and again, an OH can be a hydrogen bond acceptor or donor. Right, so the OHs on the silica can both donate a hydrogen and accept a hydrogen with the oxygen. So if your compound can be a hydrogen bond acceptor, then it can interact with the silica. If it can be a hydrogen bond donor, it can interact with the silica. So what's happening is we absorb the compound, our analyte, onto the silica, so it's stuck onto the silica. Now, as the solvent moves, so we're going to put this in, solvent's going to move up the plate slowly. The solvent moving, it's the mobile phase. The silica, which just sits there, is the stationary phase. How much your compound moves depends how much it's in the mobile phase, the solvent, versus how much it's in the stationary phase, the silica. So the tighter the compound binds to the silica, the slower it moves. So we're using two solvents here, ethyl acetate and heptane. Ethyl acetate, if you just look at the universe of solvents, is fairly nonpolar, right? So look up the structure of ethyl acetate. Heptane is just a completely nonpolar hydrocarbon, C7H16 in a chain. All right, there's no hydrogen bonding, there's no dipole, it's just very nonpolar. So heptane is our low polarity solvent, ethyl acetate's a little more polar. Again, if you compare ethyl acetate to water, ethyl acetate's essentially not polar at all, really. Ethyl acetate doesn't dissolve well in water, but it is more polar than heptane. And so by adjusting the solvent, you can adjust how fast things move on the plate. So again, right, if I use heptane alone as the mobile phase, then the only compounds that are going to move are the compounds that are just completely nonpolar. All right, so you could hit pause and go look up the structure of nitroaniline, 4-nitroaniline. You could go and look up the structure of acetophenone. All right, and make a prediction. Which do you think? Hit pause, look up those structures, or, you know, this has got another minute or so to go. You could think about how fast these should move. Take a look. I might have chosen too fast of a, I might have chosen my solvents badly, right? The more polar the solvent, the more polar your eluent, the faster all the compounds are going to move. And the reason for that is, for organic molecules, you're never going to use solvents that are more polar than the silica. The silica gel is going to be more polar than the solvent. The more polar you make the solvent, the more compounds will come off the silica and the faster they'll move. So if you imagine, right, the solvent is moving so fast. It's going to, let's say the solvent moves 4 centimeters up the plate. If a compound just completely doesn't adsorb to the silica and only stays in the solvent, it will move 4 centimeters. If a compound doesn't dissolve in the solvent at all and only stays on the silica, it won't move. Most compounds are going to be somewhere in between. All right. Like I said, I wanted to shoot this video yesterday. I didn't get it done, and I've kind of made up the solvent. And looking at it, I think I've screwed up. Oh well. You want to let the solvent front. I have old eyes, so I sometimes have to lift my safety glasses. You guys should not do that. You don't want to pick the TLC plate out with your hand. You want to use a tweezer. You guys probably don't have, I definitely don't, you guys probably don't have good enough hands to do that, so I'm going to use a tweezer to go in and pick out this. All right, there you go, look at that. Now, immediately, as soon as you pull that out, you see where the solvent has run to? I'm going to mark this, we call that the solvent front. That's how far the solvent moved. And the reason you mark that, that's as far as that's as far as any compound that you put on the plate could go, right? There's no way for the compound to outrun the solvent. All right, so I'm going to look at this with my, I'm actually going to let it dry a little bit. Always let it dry. Okay, so I'll circle these in a minute. Let's see if we can. All right, so there's the plate. All right, you see that? Can't get this. Camera's a little behind. All right, so the left is, well, one lane is the mixture. The middle lane is nitroaniline, and the other far lane, the way I'm looking at it right now, it's left is mixture, middle is nitroaniline, right is acetophenone. All right, I would have liked to have gotten better separation there, but I didn't. And what that shows pretty clearly is the mixture has both compounds in it, right? It's a mixture. So I've got both acetophenone and nitroaniline in the mixture, and I'll show you. Let me turn off the light. I'll circle these. The other thing is you can just see the yellow spots, right? They're next to each other. So it definitely shows that I have nitroaniline. You might need a partner to help you with this. So I don't know if you can see what I'm doing. Like I said, I'm not a I'm not a director. I'm not a good artist. I need to write with my left hand and I can't do it. So anyway, I'm going to shine the light on here and I'm going to circle the spots. And then make sure you turn this off. I just irradiated my hand. Nice, don't do that. Okay, so here's the TLC. You guys see that? Yeah, you can see that. Right? Acetophenone is on the right, nitroaniline in the middle, and the mixture on the left. The mixture clearly has those two spots. Now, to measure the RF, which is something you're supposed to do, you need a ruler. So I'm just going to set the baseline at 10. You guys can measure stuff. Hopefully, here, I tell you what. Maybe that'll be a little better. So I'm going to set the baseline of the ruler at 10. First thing to measure is the solvent front. Oh, I almost got 5 centimeters. So it's 49 millimeters. The solvent ran 49 millimeters. And then you want to take a line, the center of the spot for both of them. So for nitroaniline, it's 22 millimeters. For acetophenone, it's 27 millimeters. Okay. You should be sketching this in your lab notebook because you're going to need to turn that in. All right. So the RF is simply how far the spot traveled divided by how far the solvent mixture traveled. I can't use my calculator because I'm recording, but the RF of nitroaniline is going to be 22 divided by 49, just under 0.5. Okay, you guys would actually go and give us a number. RF will always be between 0 and 1, right? If a compound does not go into the solvent, the mobile phase at all, it doesn't move. So its RF is 0. If a compound spends 100% of its time in the solvent, it moves with the solvent front, and the RF would be 1. Most compounds are going to be somewhere in between. Like I said, I would really like, if you go and look at the structures of nitroaniline and acetophenone, which you should do, acetophenone can be a hydrogen bond acceptor, but it can't be a donor. Okay, and so it winds up, it's got a decent amount of dipole. So nitroaniline, on the other hand, can be both a donor and an acceptor, and it's got a pretty strong dipole for resonance reasons that you guys might not see until Orgo 2. But H's, generally any compound that can be a hydrogen bond donor and acceptor is going to stick to the silica gel better than one that can only be a donor or an acceptor. And so then you would expect, like, if a compound was a lot less polar, it would move up here. More polar would be down here. So in normal, what we call normal phase, silica TLC chromatography and organic chemistry. So we've got silica as the mobile phase, silica as the stationary phase, less polar solvents as the mobile phase. More polar things run toward the bottom, have low RFs. Less polar things run toward the top. That's 25 minutes of TLC. That's enough for you guys. All right, I'll see you in the lab on Monday.